Everyone decided.
No, at least I got
decided. Oh, it's.
And you know the spurious points.
So you may not know that. What is spurious points?
Yeah.
What's this one?
Every one of my
Oh
classmates.
Oh. Yeah.
Yeah, I have
The last 2 weeks, everything is new.
And all the exams are.
Yeah. Right. Literally, there's like 5 exams.
It's like we're going on a long break out.
Long. Long.
Which one are you going on?
Probably you.
Everything else is.
So anybody else have the homework 10, the by hand part? I know I got a couple emails from students. And I have a few up here, but I have more than a few plus a couple students in this class. So who's holding out on me? Some matrix stuff?
Yeah, email it later.
Yeah. When was that due?
11:59.
Oh, tonight. Oh, never mind.
Not that terrible.
Yeah, all right. I'll shame you on Thursday. Don't worry. Okay, so today, another instance of me thinking, what the heck do I actually want them to know about linear algebra? And because when I started putting all this stuff together, it's like how I was trying to like recreate in my mind. Oh, I need to plug in the trying to recreate in my mind what 551 looked like, and I realized maybe that's I guess yes, I realize that's not necessarily the way I ought to do business, because in my experience, folks who have had 551 haven't actually known the things that I want them to know about matrices. And so this is a good chance to just do it the way that I think it ought to be done. And we'll learn as we go. But quick review. What was the last thing that we did? Last exercise, which you didn't have a homework for, mind you. So happy weekend that you had without, right? Don't worry, you'll get Senpai on the homeworks for today. So I'll have a homework for this hopefully and I get to do that while they're watching paint dry in Reactor Lab today. Great, you'll get it. Okay. So last time we played with Senpai, and we used Senpai to do all sorts of symbolic stuff. One of the things that we did was to solve systems of linear equations symbolically, right? Although you can do it with nonlinear equations, and we did some expression simplification, but really I introduced it at that time because I think it'll be useful for anything that we could call pen and paper work going forward can just as easily be done with SymPy. So if you want to translate the sort of logic that you typically have with pen and paper work on problems, you can translate that directly to Jupyter Notebooks with SymPy and come away with the same set of tools, right? And it's a way that you can do your work more cleanly. If for other classes, hopefully it becomes a way that you could do your work. For some other classes, maybe it's a way that you check your work. Okay. But it was all in support of our focus on this thing here, AX equal B, linear systems, right? So we have this matrix, we have a vector B, and we're trying to find the vector X that satisfies this. We've talked a little bit about where these matrices and systems come from. We talked about the most fundamental algorithm for solving this, which is called what? What is the most basic algorithm for solving AX equal B? Eliminations, right? Which is the subject of today's homework, the one due today, right? Yeah. So in class we did the elimination, and what strikes me as odd is the emphasis on elimination in a class like 551, because you did elimination over and over again, right? To get to reduce row echelon form and so forth. And the end result is good. I don't know that it's that important for you to get so much practice playing with 3x3 matrices. Maybe I'm wrong, maybe I'm naive. Did anybody enjoy that? I don't think so, right? Is it important to be able to do it? Yes, but it's an algorithm. And what can you do with an algorithm? You can follow it. A set of directions that if you can read carefully, you can go through and solve it. But more importantly, for the largest problem, you can give that algorithm to a computer as long as you can implement it in code. And you did that, or you summed it for the homework that's due today. So what we want to talk about today are those cases in which doing business as sort of, as we've seen so far, might not be the right way to do it. Okay. For small systems, 3x3 pen and paperwork, SymPy type stuff, it's going to be good. In general, you can't go wrong with np.nlg.solve or / in MATLAB for solving systems. Probably the most important thing is that you can take the problems that you have in your various classes and future work, and put it into the form needed. Okay, you get the tools from this class. I can't give you all of the problems or all the situations that would lead to a matrix. That'll come from some of the other classes, I hope, and I'm hoping my colleagues will support your continued use of some of the tooling. But there are some cases where we really actually have to do something different for AX equal B. And I have so this is actually a topic that I have covered, at least in part, in ME 701, which I've always viewed as sort of my boot camp to technical computing for more advanced students, maybe first year grad students. But I think it's a topic that belongs here too, because you will get to problems in your undergrad careers that fit this pattern. Right? You'll all take heat transfer, and in the past, heat transfers had some computational exercises that involve matrices that will satisfy some of the features that we look for today, namely lots of zeros and sparse. And in fact, having a lot of zeros or being sparse is something that we saw on day one of matrix, right? Because that first tridiagonal matrix that we found with the 1s and the 2s was sparse. And so that actually will be the matrix that drives a lot of the discussion today, okay? So to start off everything, we're gonna figure this out. How do we know whether AX is actually equal to B? I think it was Alex who answered me the last time I asked that. How do you check that is true? If you have A and you have B and you think you have X, how do you know X is the solution to that equation? You plug it in, right? What do you do then? If you plug it in, you hope that AX gives you the same values as B. But you've got to be able to assess that numerically. I mean, we can eyeball for simple things, and if it's like a very simple system, maybe it has to be identically equal to B without any ambiguity. We've got to figure out a systematic way to assess that closeness. Okay. We're also going to look at sparse matrices and discuss why they show up everywhere. Why do we have a whole bunch of zeros? What happens to the storage, and what happens to the complexity of the things that use sparse matrices, which I will tell you, almost all applications in engineering that base themselves on matrices, those matrices are sparse. There are rare cases where matrices in practice are dense. The first one that comes to mind is quantum molecular dynamics or other quantum type things for solid surfaces. There's a researcher in the chemical engineering department that uses something called density functional theory, DFT, if you've ever heard of that. Basically, you model cells of atoms in solid configuration. So if I wanted to figure out how is zirconium hydride, which is the moderator of our reactor fuel, okay, how does that lattice of atoms vibrate around, right? With accounting for the nuclear force, all of the electrons, everything, right? How do you do that? That turns out to be a gigantic, highly dense system. Right? You have all sorts of entanglements and so, but that's the only place that I can think of where dense matrix operations are like the fundamental. Okay. We're also going to look at alternative ways to solve AX equal B, ones that are closer to what tends to be done in practice. No matter what, elimination or Gaussian elimination, as it's more commonly known, is always going to be the first and most fundamental algorithm for solving AX equal B, even when we have sparse matrices. We're going to show how elimination can get us into trouble, even though we think we're being nice with using sparse matrices and so forth. But if we can't do elimination, then we've got to do something else. And so we'll start off with sort of a physics-oriented way of doing business, and this will lead into a set of algorithms known as Richardson and Jacobi and Gauss-Seidel iteration. These are names that you'll probably see them later on, but I want to establish them now so that you're at least aware of the concept of iteration. And then all these methods that we talk about are so-called stationary. They're going to take us from one state to the next state. What is the state going to be in this lecture? That state's going to be, we drop a neutron at one of these random walk sites. That neutron can go to the left or to the right. It only goes to the left or to the right after we take a step forward in time, right? So we're going to actually treat this as a quasi time dependent problem, where at step 1 times 0, we drop it at location 1, at least for our escape probability. Oh, and by the way, I'm almost done grading the projects, and so far they look quite good. If I have time, I'll talk about some issues that I saw in the homework, but otherwise that went pretty well. So I think my system is, I'm getting it together, which is nice. That should make my life easier. It should make it easier for me to turn these around rapidly. Okay. And then the very last thing that we'll do is talk about how these stationary methods, right, are kind of limited, and it will give us a sneak peek at so-called Krylov and Krylov subspace methods. And it's Krylov subspaces where I think there is a need to understand something about vector spaces. In fact, that's probably I feel like maybe we should let the applications drive what we learn. And for the case of problems where iterative methods are needed, Krylov subspace methods are kind of like the modern option. They're the ones that we use in practice. And it doesn't take a lot to understand why they work. It does require, though, that we dive into vector spaces, which will take us also through a tour of orthogonality, orthogonal matrices, orthonormal matrices, orthogonal projections. Some of these things that if you've all had math 551, you heard these terms, but I think we'll use these terms and let them be driven by the applications. Maybe that's the engineering way. Yeah. In fact, so I made 2 decks. We'll leave that here because I don't know what that lecture will be called yet. All right. So how do we know that AX is equal to B? And I apologize in advance. I did my best to get all my matrices and vectors in bold, but I think I have missed it because it takes that extra /math BF to do that. And so I think I'll have that missing in the later slides. But how do we do this? I feel like we actually went through an example of this a little early on in the class. But maybe my memory mistakes teases me. If I have A, a matrix, X, a vector, and B, a vector, how do I establish that AX equals B? We've said plug it in. Okay, so if I have A and I have X, well, I can take A times X, and let's call that B prime. Right? How do I know that B prime is equal to B? I need an algorithm. I need something that I give to the computer to do this, or a set of steps that you would do with your calculator. Isaac? Idea?
What are you saying before?
I'm saying that if I have just a vector B and I have B prime, which is that is my A times X, right? If I've got these 2 vectors, how do I tell if they're the same?
Check. Tree. One more.
Yeah, so I could loop through. So something like for I in range len B, and then something like assert B I equal B prime I, that something like that. Maybe we wouldn't use an assert statement. Maybe we would add up the differences or something like that. Another.
Could you use an inverted matrix? A?
Well, so we would, if we have solved for X, in effect, we have computed A inverse. We'll talk about A inverse a little bit later. But if you remember what we actually did with elimination is we said that A is equal to LU, and then we did that. In fact, you've done that for today. You get the L and the U. And so the B would actually be equal to U inverse L inverse, sorry, X would be equal to U inverse L inverse times B, right? this is the one matrix, many scenarios story, because whatever the value of B is, as long as I have U and L, I can get the X, right? I can compute these once. These don't depend on my right-hand side. If I just did like normal A inverse, then I would have to do A inverse for every single value of B. So I'll tell you up front, you should never use the inverse, right? It's useful for double checking work, but in practice, you would use the LU decomposition. Okay. Although, of course, I will use the inverse function sometimes, but just know that in general you would not. Okay. So, but this is after we've done the solution. So suppose we've done this, we get X. How do you verify that your U and L inverse were the right things? Like, how do you check that your elimination in your homework was done properly? Okay, this is one thing that you can do. You could also do something like maybe initialize a sum equals 0, and then what if you did S plus equal, let's say B I minus B I prime with plus. Would that work?
Theoretically, it could
Why would that fail?
if happen to have only two differences, and those two differences each other and then cancel out.
Yeah, so sign in this case matters. So what if I put absolute values bars around that? Would I run into that issue now? If I added up the sum of the absolute differences, I would get a number, and then I would say assert S is equal to 0, or I could, if I wanted to account for the numerical round off that is typical of just about anything we do, right? I might do what you've seen in the worksheets. I could say assert the absolute value of S minus I don't know, 10 to the minus 12. Assert that the absolute value of S is less than 10 to the minus 12 or something like that. You add up all those the individual errors or individual differences and make sure that their sum is less than some number. That I think that actually ends up putting into one number what you suggested, right? So everybody follow that. Okay. Is this the only option? Right? But we use the absolute values because that got rid of the opposing sign issue, right? You could have sort of favorable cancellation of error that would trick you into thinking you had the right answer. This gets rid of that error, but is that the only way that you could get rid of the sign error? Sign as in SIGN. No, I'm seeing a head shake. Why?
Like square.
Yeah, you could square it. I mean, if absolute value of this difference is a positive number, or at least non-negative, then so would its square, right? In fact, any power would satisfy once you put the absolute value, right? So let's keep that in mind. So this is the basic idea. We would want somehow to look at the element-wise deviations, and then because having a whole bunch of them doesn't really help us make one answer, we would have to combine them in some way to get one number that represents close or not close, right? And so ultimately, we are looking at this called the position. Actually be a function of a vector x, okay? So we know what b is. We compute a times x, thinking that we know what x is, and then we get this residual vector. Now, this residual vector is a vector. If we want to boil that down to one number, like this, we could put it into a for loop like this. So rather than looping with b I and b prime I, it would just now be the r, right? Ri. Okay, so what happens if Rx is equal to 0? And this should be, I'll be more careful with my vectorized business. Math, bold, font, math, bold, font. Apologize because this actually matters. To insert, I hate that fucker. Key. All right, math. The R. There we go. No, no. Whew. All right. So we get this residual vector. If it is equal to 0, and that should be a bolded 0. Now the thing is, I can read it and I know what it says, but I want to make sure that it's very clear to you. So if this residual vector is identically the 0 vector, no problem, right? But if it's not due to numerical error, and we just want to find something that is close enough, right? And like if we solve this with NumPy then L.solve, there's no guarantee that it will be identically 0 because there is something called numerical roundoff. We've explored that a little bit. We've talked a little bit about it. Okay? So in practice, what we hope for is a small R. Depending on the algorithm, we might make that really small or maybe not so small. If we're using Gaussian elimination, we'd expect it to be pretty darn small, right? Like we maybe not machine epsilon, which is the smallest difference between 1 and the next largest number in our floating point system. That's about 2 times 10 to the minus 16, right? So very small differences. We can resolve differences, but we would look for something maybe bigger than that, but still maybe it's very, very small numbers. Okay. But how do we do this generally? This is one option, but it's not the only option. We can have powers. So another question, is this actually equal to the error? This is the residual. Does this actually define the error? What would the error be defined as? What's that?
Plus minus the residual? Or
No, good guess. So the residual is important and it's related to the error, but what is it that we're actually trying to compute when we write an equation like AX equal B? What is the unknown? X, right? So the idea is we've solved AX equal B. We want to verify that what we get as X is the right answer. So that means that there's some true answer X that maybe we don't know. Maybe we've only, using a numerical scheme, there's always going to be some chance of numerical error, right? So what we would have is maybe an X star is the true value. And given this, whatever we think is our guess, so let's call X our guess or our best estimate. Then the actual error is going to be between X star and our best estimate, right? The thing that we get out of the elimination or whatever else we're doing. Okay. This is the residual. This is the difference between A times X and B. That's not the same thing as X minus X star. Would you agree? The only time that they are equal is when A is a very special matrix. What matrix is that?
Eigenvector.
No. What's the simplest? What is the case where A times X would be the same thing as X? The identity matrix, right? Which of course is if you have the identity times X equal B, you don't have a system at all. You have inequalities. There's no solving to do. Oh no. All right. How do we measure small? Now this puts into mathematical terms exactly what we just walked through in words on the board. We can add up the powers of these individual elements. So this is for a single vector, but you can imagine plugging in our residual or the difference between B and B prime. All that would be the same. These are 3 options. The first one is the sum of the absolute values. That's actually the first one that we did. That almost seemed natural. Of course, then we have the squared terms. And if we want to get a single number, we would take the square root. Now, we don't have to take the square root because whatever that number is should also be small, whether it's squared or the square root of it. But the definition for these things follows this pattern there. If I have the double vertical bars with the vector sub 1, right? Then I sum up the absolute value of the elements of B raised to the 1 power. And then I take the 1 root, which is, there is no 1 root, right? So you just add them up. Now, if I take B with the double vertical bars sub 2, right? We're going to add up the sum of the squares of the elements, and then we're going to take the square root of that sum. You don't see the absolute values here, once you square your positive value. Another one is if we do sub infinity. Well, that's actually going to just take the maximum absolute value of B. Now, what's interesting is this actually follows this pattern. All of these are called P norms. You might have heard the term vector norm, right? Because the vector norm is how you define the size of a vector, right? That's how you take all the elements of the vector, boil it down to just a single number. So same thing that we do for vectors in general is exactly what we need to do to quantify residuals and errors. But if you think about this, I could define the 3 norm, which would take the sum of the absolute value to the of the values to the 3rd power, and then we take the cubic one. And if you take that to the 4th, to the 5th, and all the way to P, to infinity, what happens? If you take something to the infinity power, you got a vector V with a bunch of elements, and you take it to the P power. Which one of those elements is going to blow up beyond all the others? Whatever the largest one is, right? If I've got a 2 and I've got a 5, 2 to the infinity is a big number, but 5 to the infinity to me is a bigger number. And that's the one that's going to pop out when you take the 1 over infinity root. That is the only thing selected. Now, sometimes definitions like that are a little abstract because then you're bouncing to infinity and back. But just hopefully this seems clear. So you can define norms that have p-values of all the integers 1 through infinity. There's actually a 0 norm, which just counts the number of non-zero elements in an array. Yeah.
You said the 1 over it.
Yes.
Wouldn't that just be 0?
1.
It would be 1.
Yeah, it's kind of bizarre. You have to take it in a limit. As long as you can imagine the biggest element in the array is the only one that's going to be left over, then you're good to go. Okay. So you can have these are all forms of the P norm. These are the only 3 that I see used in practice. Okay. I would say that the 2 norm is the most important norm. Right? It's the one that we've been using for all sorts of applications as we've gone through math courses, engineering courses. It has a couple different names. It has the 2 norm. Sometimes it's called the L2 norm. This would be the L1, the L infinity norm. I don't know what the L stands for. It's also called the Euclidean norm, right? Because it follows Euclid's geometry. It's how you find the distance of the hypotenuse and so forth. Okay. So now, armed with this definition of a vector norm, we can ask for some sort of stopping criterion like this. So if we are solving AX equal B through some process that's iterative, maybe it's not just once and done, we're going to get a residual that we can index with K. So we're going to get a first guess, and that'll lead to a residual R0. Then we're going to do something, maybe refine our guess and keep going and try to get a better and better solution. And then we can check this. So the relative residual, right? So that would be the residual. This would be B minus B prime. Then you divide by B. This should be less than some tolerance. Okay. We don't have to divide by B. It depends. Sometimes it makes more sense because of units, scaling. It kind of depends on what you intend this tolerance to mean. Do you want it to be a percentage difference? Do you want it to be an absolute difference? But either one would be fine. You could have either the residual divided by the magnitude of the right-hand side B or not. The principle is unchanged. So this is how we measure small versus large when it comes to a vector of residuals or any vector. So if X star is the exact solution, then the error vector, right, after K iterations, I mean, I know that might seem abstract because we haven't actually done an iteration yet. But when we do, we can define the K error. Now the problem is we don't know what X star is. If X star is the true answer, we're only going to know that if we solve it with an exact method. Maybe we can, maybe we can't. Okay, but we can always compute the residual, which is why the residual is so helpful. So there is a relationship between that residual and the error, because if the residual is B minus A times X, well, if we expand and say that B is equal to A times X star, right? That's because X star is the solution, then we end up with A times that error, right? So the residual is equal to A times the true error, which means that I could get the error given the residual. How? If I know what RK is, and I start off with my matrix A, I'm always one step away from getting the true error. How do I do that?
I didn't,
What's that?
find part A, I think.
Yeah, well, it's a matrix, so the divide is actually an inverse, right? A inverse. But what's the what's wrong with that? There's nothing wrong with taking A inverse of both sides and get the error, but what's the problem?
That's all what's word.
So if we're solving AX equal B, we hope that we can do A inverse, right? So let's assume A inverse exists, otherwise we wouldn't be solving AX equal B, right? We'll talk about the occasion where A can't be inverted, right? But I'm going to wait for the application to bring this in, not just a contrived textbook like here's the null space, right? So how do we do it? Or why would what's the issue? What are we trying to do in the first place here with this potential iterative scheme? We're trying to find X, we're trying to find AX equal B. So if we got to this point for iteration, why on earth would we spend the time to take A inverse? We would have done that from the get-go. The whole point of all this is to avoid taking A inverse. Right? We're doing this, we're taking its LU decomposition, etc. So if we knew what A inverse was, we'd be able to do this and then establish this relationship between the size of the error and the size of the residual. So this can be useful if you're double checking things, but in general, the rest of this lecture should be, we'll go through it with this assumption that we don't know A inverse and we don't wish to compute A inverse. Because as you found, doing all that elimination kind of sucks, right? Well, it sucks for the computer too, and we'll see why. Okay, so the residual is always computed. As long as we have A and we have our iterates X, we can get the residual. Usually the error cannot be unless we solve the original problem exactly, but that's what we're trying to avoid. Good to be able to verify, but not what we do in practice. Sometimes we can condition A so that the relationship between these two things is easier. And that would be taking A and multiplying it by some other linear operator, some other matrix. That would be called a preconditioner. And that would be something that we see at the very tail end of the slides today. Yeah. So this establishes some nomenclature. What I want to do now is go back to the application that we've seen before, which is this 1D random walk. So we've got the random walk, we've got a scattering ratio C, and we're going to do the fixed step thing, right? So you've all done that project, and like I said, I'm almost done, and the project looks good. I think the average will be better than maybe the worksheet averages have been. So kudos on that. Okay. Each step, a fraction will go to one or the other neighbor, and that'll be isotropic. So we'll go 50% to the left, 50% to the right. And then we'll be injecting this neutron at a given location. So we will go through, we have n cells. The problem that we had done before is to inject neutrons into cell I equal 1, and then compute the probability that they end up over at I equal n, correct? Okay, so the process that we're actually going to model now is slightly different. We're going to drop a neutron at one of these cells, and then we're going to step forward in time. And when we step forward, that original neutron is going to split into half going to the left, half going to the right. But we're going to inject another neutron at that site, okay? And so when we step forward again in time, we're going to have a neutron that was landed there. The original neutron had been gone to left and right once already. Now it's gone once and twice. So what we're going to end up seeing is the spread of the neutrons landing at our original site over to wherever the neighbors are. So it's exactly what we had been, like it's the same physics that we used before, only now we're going to walk with it in time. Whereas before, you effectively were looking at what happened at time equal infinity, when you average over all of the neutrons that are injected at cell 1. What's the probability that they get to the end? Now we're actually going to march forward in time. Okay? So what this is going to look like is this problem. B is going to be that forcing function. So if I've got n equal 0 through n, 0 being one boundary and then n being the other boundary, if we put them on 1, we'll have a 1 in that location of B. Okay. Then we will have this matrix P. which tells us something about the probability that a neutron that lives in a location gets transferred to the neighbor. So this is going to be the move neutrons evenly to the left or the right. And we'll see what that matrix looks like. And then C, of course, is going to be the scattering ratio. If C is equal to 1, then this is just B plus PX. C is going to usually be less than 1. And the matrix P that moves these neutrons to each neighbor is going to be sparse. Okay. So what does this matrix look like? So first of all, I've got two functions here. This is the random walk function to make P. So random walk P. I've got an off diagonal of 0.5 because I am splitting to the left or to the right with equal probability, right? This is the isotropic case that we considered, okay? And then I'm using something called sp.diags. So let me do the following. First of all, I'll run this, but I want to take a look at P. So I'm introducing here some things from SciPy. This is the first time I think that we're using SciPy, with the exception, did I use SciPy for the error function? Or did we use the math module? The math module has the error function, SciPy has a bunch of special functions too. Okay, so what we have is the sparse module, which has a number of data, I guess you could call them containers or types anyway, for representing vectors and matrices that are sparse. Okay, this is just an example. I'll walk through what these mean in as we go through. But if I take that, it's a compressed sparse row sparse matrix of D-type float 64. It has 8 elements stored with a shape of 5 by 5. So just with this little bit of data that's printed out, what size matrix is P? 5 by 5. Okay. It has 8 stored elements. All right. So if it's 5 by 5, how many elements does it have? Total. If I were to write it on pen and paper. 25. It has 8 stored elements. Okay. What does that mean? What kind of elements is it going to store? The non-zero elements. Okay. So what fraction of this is filled? In other words, what fraction are non-zero? Divided by 25, so roughly a third, by 33%. So that means 66% or so are zero. This is for a small problem. What we're going to find is that ratio actually goes much closer to 100% for a very large system, right? It's kind of a, you know, sort of like the surface area to volume ratio. The bigger your volume, the smaller your surface area is relative to the volume. Okay, same thing with the size of the stored elements in a sparse matrix as you make that matrix bigger. Okay, so what does this look like? Well, it's probably not easy to look at it in this form because, well, it's something special. But I can take that and make it into an array, right? So P here and A are these specialized SciPy sparse matrices. I can turn them immediately into the familiar NumPy array by using toArray. If I look at that, you can see what this matrix looks like. Now, if you think about it, if I have my array of X values, which represent, let's say, the population of neutrons at one of these sites, it's going to take the number of neutrons that I have at site I equal 0. And it's going to say, it will not let me stay at my own site. So 0 times whatever that is going to be my contribution to my site. I do not self-scatter. I do not scatter and then stay at myself. If I scatter, I am going to the right. If I scatter to the left, well, I've accounted for my boundary condition. And I've been gone. But if I go over 1, if I'm at the second location, 50% of the time, I'm going to move to the left. 50% of the time, I'm going to move to the right. That's the P. I'll back up one slide just to make sure that, oh, there we go. So that's my P. So I'm going to take an X. The X will think of this as either the number of neutrons that live at every site or the density of neutrons. Either one would work. P is spreading those out. So if I step forward in time, whatever lived at a location X is going to show up in one of the neighboring cells, right? And that's gonna show up here. So if I wanted to, I could actually put an index where this is xk and this is xk minus 1. K is my time index or my step index. Okay? The C there is going to account for the probability that some of them are absorbed. So only the fraction C actually will be moved over. Okay. So that's P. Now, if I take a look at A, what do I see? Aha. I see a 1. I see minus 0.45. Where does the 0.45 come from? Seems like an odd number, but where that comes from something. I think you'll see it.
C 0.9.
Yeah. So if I did C is equal to 1, meaning no absorption, then I would have 1s and minus 0.5. And then we would have a matrix that looks a heck of a lot like the one that we saw on the first lecture, just scaled by a factor of 2, right? So this matrix structure, this tridiagonal, where we have 1s or some number along the diagonal, and then some usually smaller number in magnitude along the two sub the next diagonals. This shows up all over the place. Whether we're talking about neutrons dancing or heat going through a slab of material, right? It's a very, very common structure. Okay. And then finally, what do you think B looks like? Well, for our purpose, we're going to shove all those neutrons into the first location, n equal 1, right? Remember, n equals 0, the boundary, that's actually been folded already to the, I think, is that the way? Yeah. Okay, so we've got our system, 5 by 5, easy peasy. All right, so now that P matrix has non-zero only on the first sub and super diagonal. I like those the proper words for them. Okay, sub and super diagonal. So the A matrix is going to be I minus CP. That is what gives its tridiagonal shape. Okay? But both of these are sparse. So we can take a look at these sparsity patterns for different sizes. So there's a matplotlib function called SPI. There's also a function in MATLAB called SPI, and that's where they got the name. What SPI does is it takes a matrix or a two-dimensional array M, and it will show via some marker, by default a dot, where non-zero elements live. The rest will just be blank. So it gives you very clearly a picture of what the matrix looks like, right? There are probably ways that you could color these elements based on the actual non-zero value, but in this application, what we care about is the structure. Okay, so there's our sparsity pattern for A, and that's with n equal 20. And if I look at the number of elements, so it's 200 by 200. The number of non-zeros is 598. So the density, right? The density of non-zeros, or the fraction of non-zeros, is roughly 1.5 times 10 to the minus 2, or 1.5%. That's meaningful, right? I think, am I reading that right? Yeah. Okay. And if that's for this one here, which makes more sense. Here I have n20, number of non-zeros is 58, and the density is 1.45 times 10 to the minus 1, which would be roughly 15%. So from going from n equal 20 to n equal 200, the fraction of my matrix that is represented by non-zeros goes down considerably. I would go maybe to n equal 300, and I get down to only 1%. Now, there are a lot of implications for this. If I were to make this matrix on my system, I'd have no problem doing it with this size. But what if I set n is equal to, well, let's see, what if I set n equal 1,000? How many elements would there be in the matrix? Yeah, there would be 1,000,000. Okay. How much data does that require? How much does that fill up your memory? Okay, I've certainly said the numbers that you need to compute this, you know, to within a factor of within a few percent. Okay, so how many ones and zeros does it take to represent a floating point number? I've said this before. It's 64, right? Or it's 64 bits, or 8 bytes, right? 1 byte is 8 bits. This nomenclature from, I don't know if you define these, right? So we've got 64 bits or 8 bytes, so 64 bits equal 8 bytes. And we have a matrix that is n by n, and so we have n squared times 8 bytes. Okay, so if I have 1,000 by 1,000 matrix, that's how many bytes?
8 megabytes.
8 MB. All right. Your computer, do you have 8 MB of memory? Right. When we talk about bytes and things, we're talking about either the amount of memory that is the amount of space taken up in your hard drive, or the amount of memory taken up in RAM. Okay. On your machines, how much RAM do you have?
16 gigs.
16 gigs? 20 gigs? Anybody have 4 gigs? I know I've got a computer that I think most machines now will have 8. I think the 4 gigabytes has a real hard time dealing with Chrome stuff, right? Okay, so we're talking about memory in terms of gigabytes, but it doesn't take a whole lot of thought to get to something that would get, you know, a pretty big fraction of your memory stored. So what if, I mean, 1,000 by 1,000, how many, first of all, how many unknowns is that? If I have a matrix that's 1,000 by 1,000, what's the size of that linear system? Let's make sure we remember which dimensions correspond to what. How many unknowns X am I finding if my matrix is 1,000 by 1,000? 1,000, okay. Is that a big problem? Way bigger than you would want to do with pen and paper, but do you think that the problems in practical engineering computations only go up to about 1,000 unknowns? No. Let's use a very quick example. Let's consider a pressurized water reactor. What's the dimension of a pressurized water reactor? Roughly. Anybody?
Definitions?
Dimension.
Dimension.
How big is a PWR core?
17.
Right.
Yeah, I mean, we could work it out from scratch by like 1 centimeter for a pin cell. You got 17 by 17 in an assembly of pin cells. You've got 193 of those organized in some way. But let's just be simpletons and say 3 meters by 3 meters by 3 meters. That's a good enough estimate. We're within a factor of 2, I think, again, for this kind of stuff. That's all we need. So if I've got 3 meters by 3 meters by 3 meters, and I have a simulation that requires that I chop up the domain into centimeter voxels, centimeter cubed voxels. How many voxels do I have?
81,000.
What's that?
81,000.
I think it's going to be more than that. If I've got 300 meters in each dimension, sorry, 3 meters in each dimension, that's 300 centimeters in each dimension. So that's 300 cubed. I don't know, maybe you're right. What is 300 cubed? 27 million. So 300 cubed, you get the 27, and I get a 0, 0, 0, 0, 0, 0, which does look like 27 million to me. Okay, 27 million unknowns. That's n. What's the size of my matrix? Tell me how many bytes I need. How much RAM would I need to fill to store this matrix, whatever that matrix is? 27 million is my n. 5.8 times 10 to the 15. Are you kidding me? Okay, so that's bytes. Okay, so what are our or the SI suffixes?
Is that petabyte or?
So peta is 12.
Yes.
No, tera is 12.
Tera
Peta
is
is 15. So this is roughly six petabytes. Okay, who's got 6 petabytes? I just put it in RAM. If you had that, I would recommend you go on eBay and retire. Right? So RAM is so in any case, if I wanted to model a reactor, and I will tell you to model a reactor like that with centimeter level voxels is, that's not enough. I mean, maybe for some analyses you can use resolution like that, but that's after you've already done some black magic that you'll learn about in either NE 630 or in the later graduate level classes. But it's a good like thumb. But that's also not accounting for the other sorts of unknowns. That's just spatial. What else do we care about when we talk about reactors?
Temperature, pressure.
There are temperatures, there are pressures, the neutrons, if we care about the neutrons or quantify it with flux, there's got to be energy, maybe there's angle. So this 27 times 10 to the 6 for the number of unknowns can easily scale by orders of magnitude, 10, 100, you know, it's easy to go higher. So there very swiftly becomes a problem in storing the matrix in the first place. So let that be the example that defines why on Earth I would ever talk about sparse matrices. Okay. All right, so to store matrices in sparse structures, we use sci-fi sparse, CSR, and CSC. So I'm not going to get into the details of what happens under the hood, but what the key thing is, it is stored in such a way that the zeros need not be stored. Okay. The option that I'm not showing here is COO, which is actually the easiest one to understand. So I'll say that in words. The COO or coordinate format does the matrix storage in the easiest possible way. If I were to define a matrix for you and give it to you as a text file that you could read in and then use to fill a matrix, would you agree that having a 3-column CSV file where the first column is I, the second column is J, and the third column is the value to put at IJ is a good format or a simple format? Could you use something like that and fill up a matrix? If I gave you the size of the matrix, if I said it's n by n, so maybe the first line in this file is actually n equal 1,000, so it could be 1,000 by 1,000. And then if I gave you a column of I, a column of J, and a column of the values to put at I and J, you could build that matrix. It would just be a loop, right? That is a sparse matrix format. It's not the most efficient one because you don't need to store all those I's and J's. You can instead store just rows and then indexes into the columns, or you can store the columns and then indexes into the rows. Just know that these are slightly more efficient than the coordinate way. Almost always in practice, though, when you make sparse matrices from scratch, you start off in the coordinate because that's easiest for the program. It'd be very easy for me to go 4i, 4j, and get things out of the file or whatever. So these formats are just slightly more efficient and what would be used in practice. So we can actually build A without ever touching a dense array, like a regular old NumPy array. Okay, and the way we do that is to take we're producing those with the transport system. And so what we have for the internals of A are the data. So this would be like every single non-zero element that is actually stored. Okay. Then we have these two arrays. We have the indices. Okay. What do you think those correspond to? This is compressed stored row. What this actually is are the row indices, and then the is that correct? Compressed stored row. What was the size? So these are okay. So these are actually the columns, and then these will correspond to the indices for each row. So the very first row starts with the first element in my data. So I will go for data 1 and then 0, and that will be in column 0 and column 1. Then the next row starts at element number 2, but it's actually the third element, and that would start at negative 0.45, 1, and then negative 0.45. Then the next row starts at 5. So it's just a compressed way. It's not nearly as easy as the coordinate format because that usually the man, but it reduces the number of integers that you have to store, which can be painful in larger problems, right? So that's what it looks like under the hood. And so you could build these matrices by building those arrays. Okay. Now, one of the other things that matters for this, either using dense or sparse storage, comes from the actual operation. So we know that the storage of A costs n squared, right? That's what we just computed over there. And if we're not careful, we could be filling up our memory, no problem. Also, when we multiply A and B, that costs something proportional to n squared. Remember doing that when we did matrix vector and matrix multiplication, right? That scales as n squared. Now, if we go to a sparse matrix, the storage is only going to be the number of non-zeros. For our tridiagonal system, what is that number of non-zeros? When we have that tridiagonal system for our neutron bouncing around problem, we have numbers down the main diagonal and then down the first sub and first super diagonal, right? Let's approximate. Let's assume that that main diagonal, it has n elements. How many elements do the sub and super have? N minus 1, right? Let's forget about the minus 1. That is 3 times n. So the ratio of non-zeros to total is 3 times n over n squared, right? So it's a huge savings. So the matrix vector cost is going to go also as the number of non-zeros. And so that will be 3 times n, 3 times n. 3 times n is a hell of a lot better than n squared. Okay? And it's even better the bigger n gets, the disparity between the two grows. So the use of sparse stuff, you reap the benefits in a nonlinear way as you get to bigger problems. Okay? So huge benefits. Okay. Then we could do some flop estimates and let's see what this would be. I hate Zoom, right? So imagine that each one of these corresponds to the number of seconds you have to wait for a certain simulation to be done. I don't know that you'd actually want to wait 600,000 seconds for anything either, but you certainly don't want to wait this amount of time, right? These are for the identical problems, just one using sparse, one using dense, okay? Actually, very easy number to remember. How many seconds are there in a year?
3 million. Probably.
Pi times 10 to the 7.
Oh.
You're within a percent. Good. Use it at your next cocktail party. But it's also a very good way to have an order of magnitude ready, which when you have to scale between seconds and years, not an unuseful thing when you deal with radioactive decay problems in certain contexts. So keep that in mind. All right, so direct methods, which is what we've been using. Direct meaning deterministic, just keep going with the elimination and then your back substitution, right? A equal LU. If A is equal to a sparse matrix, we can still do the elimination. But in many cases, we will end up with L and U that are dense. So we actually we save a little bit in we save a lot in storage in the first place, but then we actually lose a lot of that when we do the elimination. There are algorithms to avoid the so-called fill-in, but they're not they're not magic, right? They'll give you some performance. For tridiagonal systems, this fill-in process or problem is pretty mild, especially for the ones that we've looked at. If we have 2D and 3D versions of this matrix, so just like we've had in 1D, we have one cell that has 2 nearest neighbors. If you go to 2D on a similar sort of Cartesian grid, how many nearest neighbors do you have? 4. You've got left, right, and then front, back. And if you go to 3 dimensions, you have 6. Right, top and bottom are added to that. Once you add those, you add 2 more diagonals for left and right, or for top and bottom, and 2 more for forward and back. So you get 6 diagonals plus your main center one. So you have 7 diagonals in 3D. That will lead to filling. Okay, let's take a spy dot. Oh, did I not run that? I never actually ran the. No, I did.
So there is a built-in sparse LU decomposition in the SciPy linear algebra stuff. Okay, we're not going to worry about that too much. And I see now that I was being a little optimistic with the amount of time that I gave for this. Okay, so
One quick thing about the inverse. You've probably seen the notation A to the -1 being the inverse of A. And that is equal to L times U to the inverse, which we swap direction and then we have this. So the reason that we do L and U decomposition is we can apply L inverse and U inverse easily. Why? What's the shape of these masons?
Square.
They are square, but what's their defining feature? They're triangular, like they're square in the sense that they're n by n, but they're triangular matrices because they have non-zeros down the main diagonal and then zeros either above or below, depending on which one we're talking about. Okay, so triangular inverses can be dense too,
even if the original matrix is not. So if we want to take a look at this, so this is our transport system. That's our tridiagonal A. If I look at that inverse,
does it look like it has any zeros? A was our tridiagonal matrix, right? This is still from our transport system. The minute that I invert that, I get this. So if I started with something that had only 27 million times 3 non-zeros, right, for my very, very big tridiagonal system, the minute I try to solve it, I am in the world of hurt because I can't store this matrix now. Right? If this was part of my solution to get to B, can't do it. We got to come up with some other way to do business, right?
it is useful to have access to the inversion and elimination for all systems, but what I'm going for is
something a little bit, something that we can use without having the memory footprint. Okay, so we're going to use the physics to motivate this iteration. If we have no particles, then the number of particles throughout this slab, right, at each one of these spots should be 0. And again, this should be vector, but I'm not going to waste any more time doing that. I'll update that and then upload them later. Okay. Then at each step going from K to K plus 1, we're going to add the fixed source B. So if you remember, our B defined before had neutrons dropped into cell 1, right, at location 1, and that was it. It was just 1 and then 0. Okay. And then we're going to scatter the previous populations via this operator CP. So if I have my neutron population in X at 0, I'm going to have 0. But at that same instant, I'm going to drop 1 in, and then I'm going to scatter my 0 neutrons away. So I'm just going to have neutrons at that one location. In the next step, I'm going to put new neutrons at that same location, X for I equal 1. And then the ones that were there from the first round are going to go either way. Half of them are going to go out the building because we were at the boundary. Half of them are going to go to I equal 2, right? And then we'll keep going. Now, what that leads to is this recursions relationship, right? It's recursion, but in a different sense than what we had talked about before, okay? So it's also known as a fixed point iteration, right? Where you are trying to iterate over and get it so that, well, ultimately, what do we want? We want the solution after all scattering is done. The only way we can do that is if we take K to the limit of infinity, right? We want to see what happens over an infinite period of time, putting 1 neutron in maybe per time step or per second. That is a steady state problem, right? We don't see a time derivative. In fact, we don't see time here, but K is that time step. So what we would like to see is, as long as B is sending neutrons in at a steady rate, we want to see what the neutron distribution is as when we approach whatever the steady state is. It's going to take us some time to get there, but eventually we will get there. Why? Because we already know that we can solve AX equal B. Right? We don't see an A here, but we can get an A from the P. And if we know that system exists, then this should also work. Okay, this is fixed point iteration. It's also a simple form of what's called source iteration in the neutronics. Okay, and
you won't necessarily see that unless you get to a grad level class, but the method itself is more general. So I think it fits here. Okay. So if we take a look at the source iteration procedure, we can see what happened. So these at k equals 0, so that's time equals 0. I have no neutrons. That was my initial condition of. I have nothing in the building. Okay. At k equal 1, the orange curve, you see it's just a step function. Why? Because I only have neutrons at location 0, because that's where I put them in. 0 or 1. I guess that would be a 1. Okay. When I go to k equal 2, I put another neutron in at 1, but now I have actually moved the original neutrons to the left and to the right. And so you're starting to see a spreading out of the green curve. And then over and over, as we go to k equal 25, we see this brown curve. What does that look like? I mean, if you had to describe that with a mathematical function, like what comes to mind? I think there's going to be exponentials involved. In fact, there might even be things like cinches involved. Let's see, get to see them at home with me. I'm going to keep thrusting this random walk problem at you until you tell me not to. I'm just kidding. Okay. What's that? Yeah.
Wasn't it?
Yeah, it is just, I mean, everything is exponentials. Okay. So we can do that same iteration and just put it into the terms of the other matrices. And I think this is where we'll basically leave off for today. And this lets me pick up next. Okay. So this is what we just had. This was our sort of physicsy informed iteration scheme where we're putting in neutrons at every second, and then we're propagating the neutrons at time step k to the left and right to get what our population is for the next time step. Okay. Now, if we take the matrix A and call that I minus CP, we've seen in another slide, then the equation is AX equal B. So if this thing has a solution, it would be the solution to AX equal B. That is a steady state problem, right? There's only one problem, and this is what we get when we let it sit for a long time. Obviously, there's some sort of transient stuff happening because you have to start off with no neutrons and then build a system with the neutrons, and then you wait till it stops changing. That's what you get when you solve this problem. Okay, so now we've got this iterative scheme where we can write b plus cpx is equal to x plus now b minus a times x, and that results in an update where the new x is equal to the old x plus r. What was r? The residual, right? That's the residual here. Okay. This, when you put it in this form, so usually if we're solving AX equal B, we start with AX equal B, and then we can move it around into this form. Today, we actually started with this sort of physics-driven form and then established AX equal B. But when you do this transition from AX equal B to this iterative scheme, it is called Richardson iteration, sometimes simple iteration, or in the neutronics world, source iteration. Okay. Kind of interesting, right? Because what this shows you is that we can solve AX equal B without touching inverses, right? The only thing that we need is to be able to take A and then multiply it by a vector. And now you might see why I care so much about matrix vector products, because there's so much that you can do with matrix vector products, like solving linear system. Okay. So in the I'll do this and then we'll break. Why would we expect this to work at all? Right? I'm telling you it works, but it doesn't work on conditions. For this to work, right? If we put this into the generic form with our matrix B, so x equals B times x plus whatever our forcing function is, this will only work if B has what's called a spectral radius that is less than 1. Okay. Now, we can formally talk about the spectral radius in terms of eigenvalues, but we're not talking about eigenvalues. In fact, one of the reasons why I wanted to talk about iterative methods, not only because they're useful in of themselves, but I think it's useful to talk about iteration because when we get to eigenvalue problems, the only way you can solve eigenvalue problems in general is through iteration.
Okay, we can solve it for small problems, and then if you've had the 551, you know determinants and polynomials with roots and blah, blah, blah. But if you have a system that is large enough, then Abel's theorem tells you that you can't do it because you have a polynomial whose roots are, you cannot find by hand if you have more than a fourth order polynomial. Right, so if I have a fourth order polynomial, so ax to 4 plus blah, 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 it's really nasty, but you can find those roots. You can do so for a cubic, and of course, you know you can do it for a quadratic. You go to a general polynomial with x to the 5, there is a proof from the 1800s that you cannot find those roots analytically, except in special cases. The same thing is true for eigenvalues, because there's a one-to-one relationship between eigenvalues and these roots. That means for a matrix, generally, if it's 5 by 5 or greater, you cannot find the eigenvalues, and then obviously the corresponding eigenvectors. So you are forced to do something iterative. I figure why not introduce iteration to the problem we're already talking about, ax equals b. When we get to eigenvalues, it'll be so much easier to understand, right? Because we can also do that from a physics perspective. Okay, but the key thing is that spectral radius, even though it has to do with eigenvalues, always satisfies this relationship. The spectral radius of a matrix is always less than or equal to its norm. Now, we didn't talk about the matrix norm, but it is related to the vector norm. Okay, we'll pick up that next time. Get you out of here in a couple minutes. So look for a homework on this. So I'll have you go through and actually play a little bit with these sparse things, but then I'm going to walk you through an exercise that'll be based on SymPy. And what we'll do is assess this kind of convergence, but for the simplest possible problem, the simplest linear system, the one with one equation, ax equals b, where a is a number, x is a number, and b is a number. Right, easy peasy, but I think it'll help you review some things that will be useful later on. It'll take you back to Calc 2 and infinite series. I know. Hey, this is a engineering analysis. You should expect to use all the math.
All right. I will see you on Thursday.
If